Okay, hello again. This is the module 5B in chapter 5 on probability. This time we're going to be talking about joint and conditional probabilities. So, a conditional probability. When you see this vertical bar called a pipe symbol, it's read in the statistical sense as given that. So if you see probability of A pipe B, that means the probability that event A occurs given that event B occurs on the same trial. Okay, and so we're making a probability statement about whether or not A is happening. So that's the random trial with respect to this statement. And B is something that we know has happened. It's the condition that must have held, and it sort of limits the scope of the possibilities we're thinking about. We're thinking only about cases in which B has occurred. Okay, we'll see this a lot moving forward in these next few probability rules. If you know that one event occurs, this is another definition. If knowing that one event occurs tells you nothing about the probability of the second event, then the two events are independent of each other. So if the probability that A happens given that B happens is the exact same thing as the probability of A happens when B doesn't happen or not B occurs, then we just say, well, that's just the probability of A, and it doesn't depend on whether or not B has happened. And so that's the definition of independence that's really important to bear in mind as we move forward in the course when we talk about probabilities and in general statistical independence. A lot of times people hear the word dependence and they think that if two quantities, if there's not a clear sort of causal dependence, one thing depends upon another in order for it to be possible or something like that, then they can be thought of as independent. That's not what we mean when we use the term in a statistical sense. Independence means what we're seeing right here, that the knowledge that B has happened tells you nothing about whether or not A will happen. So that's really crucial to know that there is a specialized definition of independence that we're going to be using in this course. Okay, so rule 6 in our probability list is for independent events, and it's allows you to calculate what's called the joint probability, the probability that both of them happen. So if A and B are independent, then the probability of A and B, that joint probability, is just going to be the product of the probability of A times the probability of B. Okay, so it's a multiplication rule. Some people call it the multiplication rule. So what's the probability that the next child born in the U.S. will be female and will have an odd social security number? Or consider throwing two dice. What's the probability that they will both show a 6? These might both be cases where, lacking other information, we'll assume that independence is involved between these random trials. So, if we're saying that the sex is female, it's probably around 50% at birth, and the social security numbers, as far as I know, they're sort of randomly assigned, subject to not clashing with an already assigned one. So the probability that one is odd, since half the numbers are even and half are odd, we'd say that's probably also 1/2. So the probability of both of them occurring, assuming independence, is 1/4. Or similarly, if we're thinking about the dice rolls again, probability that roll 1 is 6 and the probability that roll 2 is 6 is 1/6 times 1/6, they're 1/36. And notice, we may arbitrarily be calling one dice 1 and the other dice 2. We may not be able to tell them apart, but we can still think about them in terms of two random events. Okay, so that multiplication rule is useful, but only in this context where we have full independence. Just like in the addition rule, we had a general form. Here we have a general form of the multiplication rule that applies in a wider context. If you want to calculate a joint probability, the probability of A and B, but you don't know that the two events are independent of each other, or that you know that the events are not independent, so there is some dependence, then you can calculate that joint probability two ways. You can say, well, it's just the probability of A times the probability that B happens given that A has happened. Or you could say, start with the probability of B and multiply that times the probability that A happens given that B has happened. So this works whether or not A and B are independent of each other, and it shows up in a lot of context, right? And so this is the general form that you should pay more attention to. So what's the probability of rolling an even number less than 4, if we're going to use another sort of silly dice example? Well, rolling less than 4, that's one event. We've talked about this in the previous video. There's 3 possibilities there, so you get a probability of 1/2. Okay, what about the event the roll is even given that the roll is less than 4? So I depicted the sample space over here. The sample space of the dice was 1 through 6, but in this case we've constricted it because we know this rule that we're talking about is less than 4, so there's really only 3 possibilities at this point. So it's crucial to understand how this bar modifies things. It tells you something about what's happened, and that can affect the sample space and affect the probabilities of this event that you're talking about. So given that we're talking about a roll that's less than 4, we've only got 1, 2, 3 possibilities, and so an even number is one of those, so 1/3, right? So the probability event A and B is, the roll is even as A, the roll is less than 4 is B, so the probability that they both happen is the probability that's less than 4. Ooh, this should have been a multiplication down here. I apologize for that. I'm going to put, those are hacky attempt to make those parentheses. And the probability that R is even given that R is less than 4, and that gives us 1/6. Okay, we've worked through a few problems now, and so just to emphasize the general recipe that we're using for solving these problems, you're going to write down the data and the quantity to be calculated in the correct notation. At least that's what I recommend as the first step. So you need to be thinking about what the event is you're being asked about, what event the probability statement applies to, what's the sample space of that event. That's got to be in your mind. And then think about, was that probability statement, was it just a special case of the entire realm of events? Was it a conditional probability, that depended on some condition being true? In that case, we need to make sure to denote that with the bar and what event has to happen in order to make the probability statement true. So it's really important to write down a conditional probability in the correct notation, or to leave it undecorated if it's not a conditional probability. And at that point, once you have things expressed, then you can look at those rules of probability that are available, those probability rules of 9 or 10 rules on Canvas, and find one that matches, lets you solve for what you're lacking. But it's important to concentrate on not kind of getting ahead of yourself and saying, oh, this sounds like I'm going to add or multiply probabilities. You really have to take the time to denote things correctly, or you'll get yourself confused in a difficult problem. All right, so let's just work through a few more examples here. What's the chance or the probability of rolling a 5 on the first roll but not on the second? So not a 5 on the second. So we generally assume something like dice rolls, they're not going to affect each other, so that's an assumption. That sort of physical model of how the world acts leads us to the assumption that independence is probably justified in this case. The probability that we get 5 on the first roll, so here I'm using F for the first roll. We've already talked about how that's 1/6 in several of these examples. What about the probability that the second roll is not 5? Remember, we can do that from the complement rule, just subtract that 1 minus the probability that S is 5, so it's 1 minus 1/6, so that gives us 5/6. And now we have the probability of the first roll being a 5 and the second roll not being a 5. And assuming this independence, we can use the simple form of the multiplication rule and get that product right there, 536. But having some notification that's not going to confuse you is really crucial. You'll see students write things like, what's the probability of a 5 is 1/6. I mean, I know what they mean, and it's totally understandable that you might write that. But you're really liable to confuse yourself if you don't use some notation about what the events are when you're talking about a more complicated example. So if you've got the time, expressing it more clearly like that is really going to help you out. Okay, let's work through another example. A population has an allele frequency of 0.2 for the recessive blue eye color allele. We'll note that with a little b. What's the probability, assuming random mating with respect to eye color, that a person will have blue eyes? So the genotype is little b, little b. So you might want to pause the video now and think about how to solve this. We use a lot of genetics examples in probability, so a review of simple genetics might be wise too, just the notation. But we don't get into anything really fancy with genetics, just dominance and things like that. Okay, so let's work through solving this. Population, this is the question again. So how do I think about this? Well, I think the event genotype little b, we can think about that as a genotype, but it really means the maternal and paternal contributions to the genome were both the little b allele. So we can think about reaching into a gene pool and the maternal contribution being little b and the paternal contribution being little b. The fact that it's random mating with respect to eye color means you're sort of forced to assume that the paternal and maternal contributions are reaching into the same gene pool. So these probabilities are equal to each other. They're both 0.2, which is the allele frequency in the population, right? So how do we get the genotype of little b? We've got to have both of those events happen. And so now it looks more like a probability rule that we can search through our probability rules and solve. So it's two events, so it's a joint probability. We've just discussed why we think they're random, because it's random mating with respect to eye color. So we're just going to end up multiplying those two probabilities and getting 0.04. So we're here, once again, we have to sort of think about the mechanisms a little bit and say, translate statements in the problem like random mating with respect to eye color to this statistical concept of independence. We emphasize in this class sort of real biological type of probability problems, not just looking through the rules, but actually can you think of how to apply the rules appropriately in a particular situation. So it's important to be able to look for the signs that we can treat different events as independent of each other or mutually exclusive of each other. Okay. Here's a very similar example. A locus has two alleles, big Q and little q. If allele little q has a frequency of 10% in the population, and we assume random mating, so that means maternal and paternal alleles are randomly drawn from the gene pool, what's the probability that an individual will be heterozygous? Okay, so the way I think about that, once again, the genotype tells us something about maternal and paternal contribution. A genotype being the heterozygote, which we frequently denote big Q, little q, it doesn't necessarily mean the big Q comes from mom. It could be the maternal contribution is little q and the paternal is big Q, or the maternal can be little q and the paternal big Q, or vice versa. The maternal genotype could the genetic contribution could be big Q and the paternal little q. So we need to think about both of those ways of obtaining the genotype of that is the heterozygote. So once again, we use this random mating to say that what's going on from the paternal contributions is equal. And this is the complement rule. We were given 0.1, but from that we know the frequency of the big Q allele is 0.9, because there are only two alleles, and one of them is at 0.1, so the other one's got to be at 0.9, because in the sample space of drawing an allele, you've got only two events, and so they have to add up to 1, so the other one's got to be 0.9, right? So that's how we get that 0.9 in there, and we've made some progress. We still don't have the final answer, but it looks a lot more like a probability question. I put some brackets in here just to denote that these two go together as an AND statement, and these two go together as an AND statement. So it's like, what's the probability that the maternal and paternal contributions differ? There are two ways that that can happen, and we can calculate the probability of each of them, right? Once again, we're assuming that we're going to assume independence when we're calculating each of these probabilities. The other thing that we need to think about when we're doing an OR type statement is, are they mutually exclusive? And yes, they are, right? Because it's not possible for the maternal contribution to be big Q and little q on the same trial, right? And so that's the definition of mutually exclusive. That means that we're going to be able to just add these two probabilities together. So instead of this OR statement, we're just going to add that probability and that probability. And so once again, we're going to use the independence to say, how do we calculate this probability, this first probability that we were looking for? Well, because it's random mating, we can just multiply the two probabilities. 0.9 times 0.1 is 0.09. And the other way to get a heterozygote, the maternal contribution is little q, the paternal contribution is big Q, is 0.1 times 0.9, so that's also 0.09. So now we're ready to add them together. Remember we said that the genotypic probability was going to be the sum of the two. So we're just summing the two down here, and we get our final answer of 0.18. So I know that's a lot of steps. Let me emphasize, if you're just working through things logically and showing your thought process, we give partial credit for like extracting that from the problem and extracting that and realizing that that's an OR statement and realizing that the OR statement leads to a addition, and realizing that you need to multiply in here. So there's a lot of opportunities if you are conveying to us that you're thinking about this process clearly, that for you to get partial credit, even if you end up messing up some math error somewhere along the way, that's not going to hurt you much. So frequently people stress out a lot about these probability problems, but as long as they're very clear about how they're thinking about the problem, they get the vast majority of points, even if they don't get the final number exactly right. And that's much more important, understanding the process. Okay. Also should note that you may have learned in genetics classes or in intro bio this Hardy-Weinberg equilibrium, or Hardy-Weinberg rule, and learned p squared 2pq plus q squared. That's this 0.18 is the 2pq rule, the twice the frequency of one allele times the frequency of the other allele. And so that Hardy-Weinberg is really just basic probability rules. Okay, so let's, to emphasize why I talk so much about good notation and thinking things clearly, let's think about this example. We roll 2 dice and sum the rolls. There are 2 ways of getting a 4. You can add 1 and 3 together to get a 4, or you can add 2 and 2 together to get a 4. There are also 2 ways of getting a 5. You can add 1 and 4 together, or you can add 2 to 3 together. We know all combinations of rolls are equiprobable, so it seems like the probability of getting the sum of 4 should be equal to the probability of the sum being 5. So what's wrong with that argument? Pause here and think about it a little bit if it's not obvious to you. The way I sort of went through it pretty quickly, it didn't seem obvious to me that it's wrong. Of course, I know because I made the slides. And really what's going on is I was sort of thinking very sloppily about events. I was just saying, well, there's a couple ways of getting to 4. But really we could get a 1 and a 3, or a 2 and a 2, or a 3 and a 1. So 1 plus 3 is obviously the same thing as 3 plus 1, but it might matter what order we do things in. And in terms of rolling a 5, we could get a 1 plus 4, a 2 plus 3, or a 3 plus 2, or a 4 plus 1. So we see there's actually more ways to get a 5 if we think about the 2 dice as separate opportunities to get these outcomes. And so if you were to approach this problem and think about it a little bit more clearly about, okay, what's got to happen in order for the event that we're talking about. We can think that we were asked about the total probability being 4. Well, how is that going to happen? We're going to get some roll of I on the first roll, and then the second roll has got to be 4 minus I. Those are the situations that would give us a 4 as the sum, right? And so thinking about it in this way is clearer because we're getting down to the core events that are happening, and we can think more clearly about those events. So here's the sample space of the first event, 1, 2, 3, 4, 5, 6. And here's what you'd have to get on the second die in order to get a sum of 4. So you'd have to get a 3 on the second die, or a 2 if you got a 2 on the first die, or if you got a 3 on the first die, you'd have to get a 1. And each of those has a probability of 1/36 because it's 1/6 times 1/6. But wait a minute, if you rolled a 4 on the first die, you'd have to roll a 0 on the second die, and that's not possible on a standard die, so that's why that's shown in red, and there's no probability down here. So just thinking about it in terms of the events and not sort of sloppily waving your arms about, well, there's 3 ways to get this and 2 ways to do that. It really is clearer if you think about the random events and how they're related to each other, and you can avoid a lot of silly mistakes if you think about it more clearly in this manner. So that's why I emphasize notation so much. Okay, so the next video we're going to talk about Bayes' theorem and the law of total probability, and then we'll be done with the slog through all of the rules of probability, thankfully.